Welcome to Graphing Rational Functions. As we begin our study of rational functions, it would benefit us to first look at the rational function definition. A rational function is a ratio of two polynomials that satisfies the following equation. R of x is equal to P of x divided by Q of x, where P of x and Q of x are polynomials. Let's look now at some characteristics of graphs of rational functions. We have pictured here the rational function r of x equals 2x squared plus 2x minus 4 over x squared minus 1. And you can see the graph here in blue. The first component that I'd like to look at is a horizontal asymptote. Notice here that we have a horizontal asymptote with the equation y equals 2. And it's just an imaginary line running horizontally across the xy axis that the graph will not cross over as x tends towards positive infinity and negative infinity. Although it is possible for a graph to cross a horizontal asymptote as x is closer to 0, so closer to the y-axis. Notice that the equation for this horizontal asymptote is y equals 2 because the horizontal asymptote is going through the value of y equals 2 on the y-axis. The next component that I'd like to look at is the vertical asymptote that we have here on this graph. The vertical asymptote has the equation of x equals -1, and that's because the vertical asymptote is crossing the x-axis at x equals -1. And what's important about a vertical asymptote is that it's an imaginary line that the graph will not cross over anywhere on the xy plane. The next important component that I would like to look at is a removable discontinuity or hole in the graph. And you can see that right here. So the graph goes along and it jumps over this value of x equals 1. And so our hole is located where the point 1, 3 would have been. Another important part of our graph is the y-intercept, and that's just where the graph crosses the y-axis. Notice it's here at 0, 2. And then we also have the x-intercept, which is where the graph crosses the x-axis, and that's at -2, 0. What's important here is that the graph will only have one y-intercept, while it's possible for the graph to have more than one x-intercept. And so let's talk about why the graph can't have another y-intercept. Imagine that it did have another y-intercept. Let's say that the graph also crossed down here. So we have this y-intercept here. Would this be a function anymore? A really good visual of whether a relation represents a function or not is the vertical line test. Now, if we run a vertical line across our relation here, notice that it crosses in more than one place. So this no longer represents a function because we allowed the rational function to have another y-intercept. And so there's another branch of our rational function in this bottom right region. So it is no longer a function. So we cannot have more than one y-intercept, or our relation will not be a function. Our main goal in this section is to learn how to graph a rational function by hand. So we're going to go over the steps for that. Step 1 is that we want to determine if there is a horizontal or oblique, which is a slant asymptote, and draw it. Step 2 is we want to find and draw any vertical asymptotes. Step 3 is to find and draw any removable discontinuities or holes in the graph. Step 4 is to find and plot any x-intercepts. Step 5 is to find and plot the y-intercept if it exists. Step 6 is to plot any test points needed and finish drawing the graph. Let's look now at example 1. Here we are asked to graph the following rational function and determine its domain and range. So we have here our rational function r of x. Notice that it is fully factored in the numerator and denominator, which will help us when we get to finding the x-intercepts, the y-intercepts, and any discontinuities. It doesn't so much help with finding the horizontal or oblique asymptotes, but we can still get around that. So we did learn in a previous lesson how to find the horizontal or oblique asymptotes. If you remember, you begin by taking the leading term in the numerator and dividing it by the leading term in the denominator. If you end up with, after simplifying, some number divided by some power of x, here we'll just say x to the 1, then y equals 0 is going to be your horizontal asymptote. And I'm just going to write down up here horizontal asymptote. If instead, after simplifying, you end up with the same power in the numerator and denominator when you divide your leading terms. For example, if you have like 2x over 3x, well, you're still going to cross out the two x's when you're simplifying, and you're going to be left with 2/3. So your horizontal asymptote will be y equals 2/3. Now we learned about a different scenario. If after dividing the leading term in the numerator and the leading term in the denominator, you're left with a numerator that has 1 degree higher than the denominator, such as if you have x cubed over x squared, then when you simplify this, you're going to end up with x. And when we have that type of case, we have not a horizontal asymptote, but what we call an oblique asymptote. Oblique asymptote. And so to find the oblique asymptote, sometimes called a slant asymptote, what you would do is divide the entire numerator by the denominator. And you get the equation of the line without using the remainder, of course. We went over that as well. But you're going to divide the denominator into the numerator for that. Again, what's important here is the numerator can only be 1 power higher than the denominator. So if you have a linear expression on the bottom, then that's real simple. You can just use synthetic division. But if you have something like what we have here with an x squared, some type of expression, x squared plus x minus 1 or something like that, you're going to have to use long division for that. But that's how you'll find your oblique or slant asymptote. So let's go ahead and apply this horizontal asymptote trick down here to our function. So for part 1, we're going to be looking for the horizontal asymptote or the oblique asymptote, whichever it is. And I'm just going to write here that we're looking for the horizontal asymptote. I'm going to put HA, standing for horizontal asymptote. Okay. Now notice that this is factored out, so it's a little bit harder to see what the leading terms in the numerator and denominator are. But all you have to do is like so. So we're going to multiply 3 times x times x times x. So for each of our factors, I multiply the leading terms and any number that's factored out. So in the numerator, if I multiply 3 times x times x times x, I get 3 times x cubed. That would be the leading term that you would get if you multiplied this all out. So what I have then is r of x if we're just going to use the leading terms on the top and bottom, it's approximately, in the numerator we have 3x cubed Now we can do the same thing in the denominator. So I have x times x times x. That's going to be x cubed. Notice here that I have the same power in the numerator and denominator. So we have this second case here where the horizontal asymptote is just going to be the ratio of the coefficients. So we have a coefficient of 3 on top and a coefficient of 1 on the bottom. After canceling the x cubes, we get 3. So our horizontal asymptote then is the line y equals 3. And we can go ahead and graph that. Now for step 2, we're going to find any vertical asymptotes. And then we're going to go ahead and put them on the graph. And notice that I abbreviated VA instead of writing out vertical asymptote. So vertical asymptotes occur when you have solutions in the denominator that don't also appear in the numerator. So right here, I have a factor of x. When I set that equal to 0, I'm going to get a vertical asymptote because I don't have a factor of x on the top. X minus 2. I don't have a factor of x minus 2 on the top. So when I set that equal to 0, I'm going to find another vertical asymptote, x plus 1. Another factor in the bottom. It is not a factor in the numerator. So when I set that equal to 0, I'm going to get a vertical asymptote. So let's go ahead and do that. All right, so our first factor is x. Well, I'm going to set it equal to 0. And this one's nice because there's no other work to do. X equals 0 is one of our vertical asymptotes. So we can go ahead and put that on our graph. The next factor is x minus 2. So I'm going to take x minus 2, and I'm going to set that equal to 0. To solve this, we just need to add 2 to both sides. When we do that, we're just going to end up with x equals 2. So let's go ahead and draw that asymptote. Then our other vertical asymptote comes from the factor x plus 1. So we take x plus 1 and set that equal to 0. So we're going to have to subtract 1 from both sides to solve this, and we get x equals negative 1. Now for step 3, we would look for any removable discontinuities or holes in the graph, but those are going to only occur if you have a factor that's in both the numerator and denominator, and we don't have that here, so we can skip step 3. And then for step 4, we're going to be plotting any x-intercepts. So let's look at step 4. We're going to do our x-intercepts. X-intercepts occur when we have zeros in the numerator that aren't also in the denominator. So if you look at the numerator, we have 3 factors here, x minus 3, x minus 1, and x plus 3. We're going to set each of those factors equal to 0 to find our x-intercepts. So if I take x minus 3, I set it equal to 0. Well, I would just add 3 to both sides, and I would get x equals 3. So our x-intercept is the point 30. Remember, for x-intercepts, the y value is always 0. The next factor we have is x minus 1, so we set that equal to 0. I'm going to add 1 to both sides, and I'm going to end up with x equals 1. And so my x-intercept will be the point 10. And then my other factor is x plus 3, so I take x plus 3 and set it equal to 0. And so I'm going to subtract 3 from both sides, and I end up with x equals negative 3. So I'm going to have the point negative 3, 0 as my x-intercept. So I'm going to go ahead and plot those points on the graph. So this is the point negative 3, 0. And then here's the point 1, 0. And the point 3, 0. Now, step 5 is to find the y-intercept. Well, the y-intercept is where the graph crosses the y-axis, but notice that we have a vertical asymptote there. The vertical asymptote x equals 0 is on the y-axis. So we don't actually have a y-intercept because we know that a graph cannot cross a vertical asymptote. So there's no y-intercept here. So instead, we'll go on to step 6. So for step 6, it tells us to plot any test points that are needed. Well, we don't know if we're going to need any test points till we start graphing it. So let's go ahead and start graphing. So let's look now at the left part of the graph. Notice on the left part of the graph that we have the point negative 3, 0 as our x-intercept. Well, whenever we're graphing these, we need to decide, is the graph going to be above or below the horizontal asymptote on each part? Since we are going towards the extremities of the graph, we're going towards negative infinity, it's not going to cross over here. So we do need to decide above or below. Well, since there's an x-intercept, it has to be below because it's going to have to cross through that x-intercept. So our graph is going like this. And then it's just going to continue to go down towards negative infinity, very close to the vertical asymptote x equals negative 1. Okay, so let's go ahead and draw the part of our graph that's in the interval between the vertical asymptote x equals negative 1 and the vertical asymptote x equals 0. So notice that we don't have an x-intercept here. That tells us that the graph won't be anywhere in this little region up here close to the x-axis, but it could be below that. You could have a little upside down U shape right here, or it could be above the asymptote. And we won't know until we do a test point there. So what we're going to do is pick a test point that's between x equals -1, and x equals 0. And so our central point's actually x equals -0.5. And what we're going to do is we're going to plug that into our function r of x. So what we're going to do is find r of -0.5. And so this is step 6 of our graphing process. We are going to find r of -0.5. So notice I don't have a lot of room to show the substitution process here, but I'll just explain. Basically, r of -0.5 just means that we plug in a -0.5 everywhere that there's an x in our function r. So when we do that, we can actually use the calculator here. That's going to equal 63. So that's a pretty large number. That tells us that the graph is not in this area down here below the x-axis at all. So that tells us that our graph is not below the x-axis, it's not negative. Also, it tells us that it's above the horizontal asymptote of y equals 3, although we're not going to be able to graph it here because notice our xy coordinate plane that we have only goes up to 7. So just know that the graph is somewhere up here, and it's just going to have a little U shape up there. And I actually have a slide right after this that shows a picture of the graph if you'd like to see it. Now let's look at the interval between the vertical asymptote x equals 0 and x equals 2. We want to figure out what's happening here. Where's our graph? Well, what's nice here is that we do have an x-intercept. So we know that the graph is going to cross the x-axis here. What we don't know is if the graph is going to be going down, touching and going down, or if it's, going to come from the top and cross through or come from the bottom and cross through. So we need to find test points for that as well. So we're going to find test points in the region between x equals 0 and x equals 1, and the region between x equals 1 and x equals 2. So 2 different test points. So for the region between x equals 0 and x equals 1, we can use 0.5. That's right between those 2 numbers. So we're going to do r of 0.5. And again, you can just use your calculator here. R of 0.5 is approximately -11.7. And notice that the xy coordinate plane that I have here does not go down to -11.7. It only goes down to -7. But this still tells us that in this interval, our function is down in this region. So it's actually following the vertical asymptote x equals 0 all the way towards -infinity. So we'll just keep that in mind when we're drawing it. Now let's plug in a test point that's between x equals 1 and x equals 2. So we can pick 1.5. So we're going to find r of 1.5. And that equals 5.4. And we can go ahead and plot that point. So we have x equals 1.5 and y equals 5.4. That's going to be about right here. So let's go ahead and label our point. We have 1.5, 5.4. And then we'll go ahead and draw our curve. So it's going to go up from negative infinity and follow our asymptote x equals 0 until we get to the point 1, 0. And then it's going to continue up, and it's going to go through the point 1.554, and then it's just going to follow the asymptote x equals 2. Now let's look at our last little region here between the vertical asymptote x equals 2 and infinity. Well, we have an x-intercept here at 3, 0. So the graph's going to come up from negative infinity and follow the asymptote x equals 2. It's going to go through the x-intercept, 3, 0. And since it's not close to the y-axis, it's actually going to follow the horizontal asymptote towards infinity. It won't cross over the horizontal asymptote there. So now we have a complete graph. Our other task was to determine the domain and range of the function. To determine the domain, we could either use the formula or we can use the graph. But let's just talk about it. Well, we know the graph comes from the formula anyway. The domain is the collection of x values that are valid for our function. Notice that we're keeping out x equals -1, x equals 2, and x equals 0 because those are the solutions in the denominator here. That's what's going to cause the denominator to equal 0 on our function. And you can see that, on the graph, we have vertical asymptotes that are not included in our graph. So those are not included in the domain. And we're going to go ahead and write our domain in interval notation. So let's do that. Here's our domain. All right, so the graph, remember when we look at domain, we go from left to right. So it's coming from negative infinity all the way to x equals -1, and we have an asymptote. So we have negative infinity. We put parentheses because we don't include negative infinity. We've got negative infinity to -1. -1 is not included because it's an asymptote. So we put a parentheses there. And then we have a union because we have other little regions in our domain. We're going to pick up from there, parentheses, -1. And then we have this little region from -1 to 0 where we have another vertical asymptote. So we do not include 0. We're going to put a parentheses there. And then we're going to pick up and continue. And then we go from 0, we follow our graph from 0 all the way to the vertical asymptote x equals 2. So we have 0 to 2, and 2 is going to be in parentheses because it's an asymptote. It's not included. Then we have one other region. We have union. We're going to pick up and continue from 2, not included, all the way till, if you notice, the graph just continues to positive infinity. So we have from 2 to infinity here. And that's our domain. Now let's look at the range. We're going to find the range by looking at our graph. So the range tells us all the y values that are included in our function. Well, if you look at the left side, notice that we do have y values, from 3 up to infinity that aren't included, but that's not our entire function. Our entire function also includes these other 3 regions right here. We know that this one here, we talked about that it's, way up at the top, starting, around 63 and going up towards positive infinity. This region right here actually goes from negative infinity to positive infinity. It doesn't stop. right? So that actually tells us our range is from negative infinity to positive infinity, even though on these other little pieces here it's not. For the entire function, we're looking to see what y's are included. So our range is from negative infinity to positive infinity. We scroll the graph from bottom to top, every y value is included. So here's a graph that I created using the calculator that's a little bit neater. Notice it does look just like our other graph. The only difference is now we can see this little region here because I put the graph on a scale, I think up to 200. There's 200 up here. And so you can actually see the area that we were trying to get earlier. I think we plugged in negative 0.5. That would just be a little bit to the left of this point here, but this is the minimum of this little area here. It's negative 0.48, 62.9. So that's why we couldn't see it on the graph, because our graph that we had here, our XY coordinate plane, only went up to 7. But now you can see it here. And then all the other regions look exactly the same. You can see the asymptotes and everything. But there you go.